Hello all, my name is Eric Comstock. I'm a graduate researcher at the Georgia Institute of Technology, and I'm presenting today on external plasma breathing magnetohydrodynamic propulsion. Dr. Romero Calvo, my advisor, helped me on this research, and I'd like to thank him for his guidance. So the main objective of our research is to mitigate the problem of space debris. So space debris is one of the largest problems with near-term space exploration, and as you can see in this diagram, the majority of space debris is in low Earth orbit. That's where it's densest, and that's where most of it is. Multiple methods have been proposed to help mitigate space debris, the largest of which being deorbiting and active debris removal, but both of those require propellant. Deorbiting requires propellant to deorbit your satellites, and active debris removal, while there are multiple different options, which you can see on this slide, all of them require at some point propellant to actually drag the space debris out of orbit. And propellant is expensive to ship up into space. It's at least $1,500 per kilogram, sometimes up in the tens of thousands per kilogram, depending on your launch system. So every gram of propellant saved is a good bit of money. So therefore, in the interest of making space debris removal more convenient, we need to remove the propellant requirements on space debris removal devices. It's at this point where atmosphere breathing electric propulsion can come in. Atmosphere breathing electric propulsion is a mechanism for directly harvesting the molecules available in the ionosphere and in the Earth's upper atmosphere to use as repellent in electric propulsion systems. These systems do not need to carry onboard propellant because they can harvest it directly from the environment, and a lot of work has been done on these subjects during the last 20 years. With regards to these systems, though, there are a couple of major problems. The first one is just that they are very bulky. You see the systems on the slide are very large compared to the satellite itself. There's a lot of engineering overhead. There's a lot of system redesign that needs to happen. And finally, the second problem is just that right now these systems aren't really applicable in the same regions where space debris is located. So you can see on this diagram, we've got a couple of big belts of space debris at around 500 kilometers and 900 kilometers in altitude, and a collection of large debris objects as well. These systems only work at much lower altitudes and usually only with heavier objects because of the engineering overhead you need to design them. So with this in mind, I've developed a new method of atmosphere breathing electric propulsion that uses magnetohydrodynamic systems instead of a collector ionizer and conventional electric rocket engine. So this is the magnetohydrodynamic or MHD drive, and here's a cross-section showing that it consists simply of electrodes, a magnet, and a backing plate. This is something that can be attached to the exterior of a spacecraft and is very, very low in the amount of engineering complexity that needs to get started. The electrodes are going to generate a plasma current between them, and the magnet will generate a magnetic field, which will generate a Lorentz force on the plasma surrounding the spacecraft. This Lorentz force will generate a counterforce on the spacecraft itself, which then can push the spacecraft in almost any direction. This works especially well for deorbiting and active debris removal because there's a secondary force generated by the induced currents from the magnet's motion, which augments this counterforce and acts as a magnetic drag. From here on, I will be referring to the counterforce from the Lorentz force from the current caused by the electrodes as the active force of the MHD device, and the force from the current caused by the motion of the magnet as the passive force. The passive force will always go retrograde, and the active force can be aimed to point in any direction. For our application of space debris removal, we're looking at pointing both in the retrograde direction. So how do we simulate this? Well, what we did is we created a volume of space, 20 meters by 20 meters by 20 meters, and to use as a control volume with a 5-meter small sat inside of it with a 1 kilogram MHD propulsion system attached to its side. We then calculated what the electromagnetic fields would be here, and then using and then simulated the incoming plasma going into this control volume. We used no penetration boundary conditions on the sides, and then we simulated the amount of force that would be applied to the plasma, and thus the counterforce that would be necessary for the spacecraft. So there are 3 different simulation techniques that we used for the control volume expressed in the previous slide. The first of these is the 6D-Vlasov equation technique, which is a fully kinetic fluid simulation. This means that the velocity distribution at each point is tracked, which means that unlike conventional three-dimensional simulations, this simulation can simulate two different streams of plasma in the same location moving in different directions. This is possible in our case because our plasma is collisionless, which means that the velocity distribution is important for modeling it. So this is the most accurate method that we use, but unfortunately it's also a six-dimensional method because we have three spatial dimensions and three velocity dimensions. You can see the equation on the slide that we use to simulate it. But since it's six-dimensional, the amount of computational complexity was extremely high, and because of that, it wasn't really feasible for our problem, at least at the current time. So, to reduce the computational complexity, one thing that we did was we tried to simplify the Vlasov simulation based on the things that we knew about the problem. So, for example, we only really have a single magnetic potential here, and a magnetic dipole pointing in a single direction. Because of that, we can take advantage of the fact that magnets only produce magnetic fields in the directions that magnetic fields only produce magnetic forces in orthogonal directions. So since most of the magnetic field was going in the direction of the dipole, we can simply look solely at the velocity components that are not in that same direction. So this takes us to a five-dimensional Vlasov model with 3 dimensions of space and 2 dimensions of velocity involved, which then allows us to dramatically reduce our computational costs. Now the computational costs were still high, and we didn't have a lot of time to do this. So because of this, we could only do like 10, 20, 30 simulations, which meant that we could only really use it for verification purposes, not for like a full trade space exploration, which requires thousands of simulations. In contrast, 3-dimensional ohmic analysis, which uses Ohm's law and a continuous non-velocity tracking model, we could do large-scale trade space analysis for. However, since it's the least accurate simulation type, it needed verification from the 5-dimensional Vlasov equation. So with this in mind, we ended up using the 3D ohmic analysis for our large-scale trade studies and the 5D Vlasov equation for verifying the ohmic analysis. So on this slide, we are showing the verification between the 3-dimensional ohmic analysis and the 5-dimensional Vlasov equation. As you can see in this diagram, as we increase the degrees of freedom for the Vlasov simulation, it converges to more or less the same results as the ohmic analysis. The metric we're using for this slide is the effective systemic impulse, which is measured as the impulse of that's generated by the MHD propulsion system divided by the mass of the propulsion system itself. Since we're harvesting propellant from the ionosphere and not carrying it aboard the ship, we are simply using the mass of the system that we have to bring on board anyways. Since the system provides a constant thrust, this is going to increase over time, which is why we express it in kilometers per second per year. Or meters per second per year here, but it's expressed as meters per second as a specific impulse, but it's per year because it's increasing with time since we're providing constant thrust. The ionosphere is not going away anytime soon. For this particular simulation, we were just simulating the passive drag of a spacecraft in low Earth orbit. But as you can see, the Vlasov simulation and the 3-dimensional ohmic simulation converge to almost the same amount, only about 25% difference. So we use this simulation and simulations like it to verify our results from the ohmic simulation, the trade space analysis. Here, so one of the results of this trade space analysis was that we figured out that the MHD drive scaled linearly if the spacecraft scaled linearly. So, for example, if we increase the length of the spacecraft, then the mass is going to increase with the length cubed. If we do the same thing with our drive system, we increase power with length cubed, and we increase magnet mass with length cubed. Then both the active and the passive thrusts are going to increase by length cubed as well. So all the accelerations are going to stay the same. So with regards of active thrust, this we think this is the first we think this is the first time that this result has been shown for this system. However, since the MHD device operates as a magnetic sail while in passive mode, we have been able to corroborate our results for passive mode with previous literature regarding the effectiveness of small magnetic sails. Now, according to that literature, this relation does break down at magnetic moments above 1 million Tesla meters cubed, but our magnets are nowhere near 1 million cubic meters. You know, that's not flying up anytime in the near future. So since we're using permanent magnets here, we're very far from that limit, and we can just use the same scaling relation, which has been validated. Here we have the electromagnetic fields that were generated and used for the simulations. The main relevant thing here is that these were validated by COMSOL and we know that they're correct. This is just an example MHD device that's 1 centimeter wide. Now, one very interesting thing that we did find was that the plasma conductivity had an extremely important role in the MHD device thrust. So the higher the conductivity, the higher the current, and the higher the thrust you're going to generate for a certain power, because you need a lower voltage. So it turns out that the ionosphere has 2 orders of magnitude more conductivity at the equator than at the poles. We used experimental data to determine this, and we then created a model of the ionosphere using that data, which you can see on the slides here, specifically on the left-hand graph. But thankfully, despite the extremely low conductivities near the poles, we do get some applicability of MHD systems to polar orbits, not as much as in equatorial orbits, but still some, since all orbits do have to pass through the equator. So we averaged over the entire orbit what the average conductivity would be, which gives us the right graph. And as you can see, it is still 3 or 4 times lower at the poles than at the equator, but it's not 2 orders of magnitude lower like it is for the non-average conductivity itself. Now, how does the system help us? Well, it has a similar thrust to power and a similar thrust to mass as previous atmosphere breathing electric propulsion and even electric propulsion systems. But the main benefits to this are really systems engineering and the wider applicability of the system. So with regards to wider applicability, as you can see, MHD propulsion is extremely applicable throughout this entire regime where the debris is. It covers both major debris belts. It covers the large debris objects that are hazardous. So this will allow us to deorbit a lot of this stuff that the atmosphere breathing electric propulsion was not able to deorbit before. In addition, the extremely low complexity of the system means that it can be applied to missions that are already near the end of their design phase, since it's simply an external patch that you can simply attach to the satellite. It's extremely simple. It's nowhere near the extreme complexity of the other atmosphere breathing electric propulsion systems. And finally, we can just apply this in higher orbits. So we're using ions mainly to generate thrust rather than neutrals like other atmosphere breathing electric propulsion systems, and ions decay far slower than neutrals do in the ionosphere because they're at a much higher energy. So they end up at slightly higher orbits. And this gives us the applicability that we can use to actually deorbit some of these big debris belts. The other AVEP systems are only applicable in orbits where everything decays in minutes to weeks anyway, so they're not really applicable to the regions where the space debris problem is really hazardous. So with regards to next steps, the main thing that we want to do is better quantify the sources of drag. This can be through better simulations, and this can be, and when we're looking at both the application of full 60-Vlasov equations and in some particle and cell modeling. Other things that we want to do is we want to take into account the effects of device screening, which is a phenomenon that happens in low Earth orbit and other space plasmas. In low Earth orbit, this is only really applicable to large devices, since the device length is something on the order of 10 centimeters. So because of this, we expect this to be applicable to large object deorbiting cases, but not, and maybe slightly applicable to large satellite deorbiting, but definitely not applicable to CubeSats. But it is something that we want to look into. Finally, we also want to look into the potential applications of this device in inclination changes and station keeping applications, simply because those are also systems that require very low thrust for a long time. So, in conclusion, space debris is a really important problem. It's one of the greatest challenges that we're facing in the near-term space exploration. Atmosphere breathing electric propulsion looks like a great solution, but there are some there are some serious problems with it for this application. That means that it's not ideal. However, the magnetohydrodynamic propulsion is a new form of atmosphere breathing electric propulsion that can be used in much higher orbit regimes. It has a much less complex, a much lower cost in the amount of engineering that's required to add it to a spacecraft. So because of this, we believe that this is a major this warrants further study and could be a major benefit to space debris mitigation strategies. Finally, I'd also like to note that we have a very favorable failure mode. If you're using this for active drag, then the failure mode is just it reverts to being a magnetic sail, which means that even if this thing breaks in orbit, it's still going to bring the satellite down. It'll take longer, but the satellite is still coming down. And that concludes this presentation. Please let me know via email if you have any questions.